Hello, and welcome back to the course on Physics for Engineers. So, we are now on chapter 13, which is all about magnetostatics. So, before we go to the first lesson, let us first review some concepts. So, in the chapter on electrostatics, we have discussed about a single electric charge, which we may call an electric monopole, wherein the electric field, for instance, of a positive charge is radially outward. And if you have what we call a dipole, a pair of positive and negative electric charge, an electric dipole, their field pattern will look like this. So this is what we call an electric dipole. So for the first lesson of this chapter, we will be talking about magnetic field and magnetic materials. So we will try to find the symmetry between electricity and magnetism. So if there is an electric field in electricity or in electrostatics, there's also what we call magnetic field in magnetostatics. So a magnetic field, similar to an electric field, so it's analogous. It's the symmetry, it's the field version of an electric field in magnetism. So if an electric field is created by an electric charge, a magnetic field is created by moving electric charges. Or in the previous chapter, we learned that they're also called current. So basically, when your charge, electric charge, moves, aside from its electric field, it will now have a magnetic field. And the combination of these two fields is what we call electromagnetic fields. And that is basically the union between electricity and magnetism. We will discuss more of that in the next chapter. So magnetic field is due to magnetic dipoles. So in uh, in magnetism or magnetostatics, the counterpart or the analog of the positive charge is the north magnetic pole, and the analog of the negative charge is the south magnetic pole. And unlike electrostatics, where you can see a single electric monopole, a single positive charge or a single negative charge, in magnetostatics, you cannot observe a single north pole or a single south pole. It's always a pair, and the pair is called a dipole. So it's always a dipole. There's no monopole in magnetostatics. So it's always a pair of a north magnetic pole and a south magnetic pole. And the magnetic field are these lines here. So if you will notice, the field pattern of an electric dipole is just similar to a magnetic dipole. So it's just basically the same. So the field lines are going to the south pole outside of the magnet, and it's going out of the north pole outside of the magnet. But inside the magnet, the direction of the field is from south to north. So it's always the field lines are continuous. Unlike in electric field, wherein the electric field lines can be discontinuous. So in this case, the field lines are continuous. They're just moving around in circles. So magnetic monopoles doesn't exist. So there's no single north pole or a single south pole. Even if you break this dipole, this bar magnet here, exactly in half, you will create two new magnetic dipoles. So it's always a magnetic dipole. There's no magnetic monopoles. So similar with electrostatics, wherein like charges repel and opposite charges attract. So in magnetostatics, like poles repel, opposite poles attract. So if you have a north and another north pole, so they will repel, and this is what their magnetic field pattern will look like. It actually looks like they're repelling. So that's what happens when you have two north poles or even two south poles, basta like poles. They will have a repulsive force between them. they will not attract. And that's due to their field, essentially. So the similar thing happens with two south poles. But if you have a north and south pole, you're basically creating a dipole here. A north and a south will attract, and then they will create a dipole. So a north pole will always find a south pole and vice versa. A south pole will always look for a north pole. Okay, so a north pole always looks for a south pole and vice versa. Okay, so what are example of magnets? The Earth. The Earth is a giant magnet. A compass needle is also a magnet. An atom or a molecule is also a magnet. Since there are moving charges inside your atoms or in your molecules, and again, moving charges create magnetic field. So the Earth is a giant magnet. The North Geographic Pole, the place where Santa Claus lives, is actually very close to a South Magnetic Pole. And its South Geographic Pole is actually very close to a North Magnetic Pole. This These are not exact locations, but due to the tilt of the axis of the Earth. So if you have a compass, the compass is actually a magnet. The compass needle is actually a magnet. The shaded part here, that's actually the North Pole. So when the compass needle points north, it doesn't exactly point to the north geographic pole, but it actually points to a south magnetic pole. Because again, a north pole always looks for a south magnetic pole. It just so happened that the south magnetic pole of Earth is very close to the north geographic pole of the Earth. So a compass needle actually points to the south magnetic pole of the Earth. It just so happened to be very close to the north geographic pole of the Earth. Please don't confuse yourselves with the geographic poles and the magnetic poles. Okay, so all materials can be categorized into three types of uh, magnetic materials. So all materials are actually magnetic because we have electron currents in every materials. There are electrons in every materials, and these create tiny magnetic fields. We call them tiny dipole moments. And it just so happened that the magnetic field orientation of these tiny currents are at random directions, such that the net magnetic force of a material is zero. Now, if you have, so you can think of a material, say any material, as composed of tiny magnets, but these magnets are oriented randomly, such that they have no magnetic field. Now, if you expose this material to an external magnetic field, such as another magnet, so if you expose that, what will happen is the tiny magnets inside the material basically aligns with the magnetic field. So in this case, they align with the field such that one end of the material becomes a south pole, the other end of the material becomes a north pole, and then it will not get attracted by the magnet. So the same thing happen if the direction of the external field is reversed. For example, you now this is actually a nail. If you now place south pole close to a bar magnet, where in the south pole is close to the nail, the tiny magnets inside the nail will just align with the field. In this case, the magnetic field is going to the right. So one end of the magnet now becomes a north pole, and the other end becomes a south pole, and then still they will attract. The nails will attract to any poles of a magnet, to the north pole and to the south pole, because the tiny magnets inside the nail will just reorient it's the reorient themselves to align with the field. So both uh, a nail or a metal uh, will will be attracted to the north pole and the south pole of a magnet. So these types of materials are what we call ferromagnetic materials or ferromagnets. So the word ferro comes from the word for iron, so ferro. But uh, nickel, neodymium, and other very strong magnets, such as the one used for permanent magnets, are all ferromagnetic materials. So ferromagnetic materials have very strong magnetic field. So what happens is almost all or most of the tiny magnets, tiny magnetic dipoles inside the material will align with the external field. Hence the very strong magnetism. Now, we also have what we call diamagnetic materials. And an example of this are superconductors. So instead of aligning with the field, they actually disalign in the opposite direction with the field. So what happens is they will repel. Instead of attraction, such as what happens in ferromagnetic materials, there will be repulsion. So the superconductor is the one below in this GIF animation. And this is basically a circular magnet. So a superconductor and a magnet will not attract. Instead, they will repel. So that's what happens if you have a superconductor. And then the rest of the materials are paramagnetic materials. So aluminum, even though it's a metal, it has a very weak magnetism if you expose it to a magnet. Uh, And the rest of the materials are paramagnetic. Even our bodies are paramagnetic. So if you are familiar with MRI, magnetic resonance imaging, so you're basically being exposed to a magnetic field, a giant magnet. This is basically a giant magnet here. So you need to take off every metallic elements in your body. So you are exposed to a magnetic field, and the machine will analyze how your tissues, how the tiny dipole moments in your body align with the field. So paramagnetic materials, only some of the tiny magnets or tiny dipole moments, magnetic dipoles in your body align with the external magnetic field. So we are not ferromagnetic, but we are paramagnetic materials. So all of the materials can be categorized into these three: ferromagnetic, diamagnetic, and paramagnetic materials. So that is the end of the first lesson. So it's basically an introduction to this chapter. I have now introduced to you the concept of magnetic field and magnetic materials. So I will see you again in the next lesson for this chapter. Bye bye.